Okay. So today we're going to talk about measurements and visualization. This is going to be the first of two parts on this. So we're going to kind of zero in on things we should consider when we're designing and interpreting statistical measures. And we're also going to do a bit more work with data visualization and some hands-on work with ggplot to try and start to develop those chops to do data graphics, data visuals, those kinds of things. We'll spend a lot of time on that next week as well. Today's going to be a little more hands-on coding than what we typically do. Okay, so the data that we're going to be using today comes from a study published in the American Sociological Review in 2013 that looks at attitudes toward intimate partner violence among women. Obviously, this is a sensitive topic, you know, and if apologize in advance if this is kind of bring up any kind of traumatic experiences for you. But obviously, within criminology, we study intimate partner violence pretty routinely. And this is a kind of useful study to think about these measurement questions. So this is a survey across countries of attitudes about intimate partner violence. The core theory here is using a world systems theory to suggest that attitudes toward intimate partner violence have been steadily improving. That is, people are increasingly rejecting intimate partner violence across regions in the world, and that this is a function of the kind of rise of global norms about rejecting violence against women. So this is a survey, right? And from this survey, we're going to make inferences about patterns within countries. And that's tricky, right? We're going to talk to a relatively small number of people to try and make an inference about some larger population. An inference is when we use a subset of information to make a logical guess about what's happening in a larger population. And when properly designed, statistically, those inferences can be valid. That is, they can reflect the underlying population parameter of interest. A parameter in this case is something we don't know, but we would like to know. That is, what are the attitudes about intimate partner violence in different countries in the world? We're not actually going to observe that with certainty. We're only going to observe a small subset of people in different places. But if we design our study in the right way, we can get valid inferences about those cross-country averages. Okay, so the data we're going to use, I just gave you the link. You could actually just do, so if we were to go to Slack and take this link, I'll copy the link. I'll go over to R. We'll call it IPv read CSV. And then I'll just paste that URL in there. That's just coming off my Dropbox. Oh, I got to load tidyverse in first, right? Could not find function tells me I haven't loaded my package or I have a typo.
Dropbox?
I did. Well, no, so I created a Dropbox link and then I pasted that to Slack and then I copied that link from Slack.
Okay, so you can just do, you don't have to download.
Nope, I can read it straight off the web. Wait a second. That didn't work though. Let's try this again. Sorry. There was a problem in the original file. Let me make sure I've corrected it. I have. Okay, here's what we're going to do instead. I think it's probably something in how Dropbox is downloading the file. It's probably trying to be fancy and convert it to Excel or something. And that is very much what I don't want. I'm gonna put it on my I'm gonna put it on my GitHub, and then I'll put the link in Slack from there. So don't have to worry too much about what I'm doing here, but basically GitHub allows me to sync stuff between my computer and the web. It's really good for version control and for open science. That's the reason I like it a lot. Now, if we go to intro stats, slides, data, there it is. I'm going to click when I have a file like this. So GitHub is giving me like a viewer version of this, which is not what I want. But if I click raw, it'll just give me the file, which is what I want. So I'll show you how. I'm going to give you a link in the Slack to do this. I'm just kind of walking you through what I'm doing. Whenever you're ready. It doesn't want to show me this. Come on. There it is. Okay. There it is. So from here, I'm going to replace that URL with the one I just posted on Slack. That ought to work. Yes. Okay. Worked fine. Okay, cool. So there's our data. You can just copy and paste it into your read CSV command. You can see that as long as it's in quotes, I can put a URL in if it points to a CSV file and read it directly onto my computer. I don't need to download it onto my computer first. I can go onto the web and do that. I'm just going to modify my workspace a little bit to make it a little easier for teaching. Okay, so that's data's loaded in. Cool. This is a survey conducted by USAID, the US Association for International Development. And it's a survey that's part of a routine demographic and health survey. They added a few questions about attitudes, women's attitudes about intimate partner violence onto the survey. So in particular, we're going to look at 1, 2, 3, 4, 5, 6, 7 variables here. And these are the variables that are in the study. If you want to read the original study again, it's Perotti 2013 in American Sociological Review. But we have a variable that gives us within country total. So this is called, anyone want to guess what kind of data this is when we look at it? We talked a little bit about data structures last time. What's our unit of analysis in this data set? When I say unit of analysis, I mean, what does each row capture? Country year. The unit of analysis is the country year pair, right? We have Armenia measured in 2000. We have Armenia measured in 2005. Armenia measured in 2010. These are percents, right? So our unit of analysis is the country year. And what kind of data is that? Well, we have repeated measurements of the same units over time. It's panel, or we could call it time series cross-sectional, or we could call it cross-sectional longitudinal, right? But panel data is the easiest way to say this, right? Where it's we're getting repeated measurements on the same units over time. What this is good for is tracking changes within units and across units over time, right? So this way we can look at what's going on in Armenia with, just looking from 2000 to 2010. We can see this variable goes from 19.9 to 3.1, right? So even just on those 3 years of data, we're seeing a pretty clear decline within that one country, right? Okay. So we have country year data. We have a few variables here. Again, these are attitudes. These are proportions of women within the country that say this is acceptable. So there's a beat goes out that is about thinking that Intimate partner violence is acceptable if a spouse goes out without telling a husband. Burn food, similar for burning food. No media is the percent of women in each country that rarely encounter various forms of media. Secondary schools percentage of women in each country with secondary or higher education, the year of the survey, the region of the world, and the country. Okay, so we have 4 variables that are based on a survey question, right? These are individuals. So we're looking at an aggregation of individual survey results to the country year level, right? We have 2 questions about attitudes, 1 question about exposure to media, 1 question about schooling, about years of education. Okay, these are the countries we have in the data. Before I start working with something, I typically want to know what's inside of it, right? So the first thing here, I know we have country year observations. So I want to run a unique on the country variable, right? You can see that top command, unique IPv $country, will tell me what are the unique values of country in this data set. And here we are, we've got a lot. We have 65 unique countries represented in the data set, which I take unique, and then I wrap unique in a length function. So first I'm going to take this vector of unique names, and then I'm going to use the length function to ask how long is this vector, just like this. And that'll tell me how many unique countries are there. 65. And in row will tell me how many rows are in the data set, 151. So we have 65 unique countries, 151 observations. So most countries are measured 2 or 3 times. We can look at the countries by region to see where the sample is drawn from. The largest number of observations are from sub-Saharan Africa, then Asia, Latin America, Middle East, and Central Asia. Here, let's look at time. So what we have here is a sort of aggregation. We don't have consistent time periods across all the places, right? Because we only have 2 or 3 observations for each country with 130 rows. So what you can see is this kind of survey was rolled out at different times in different regions, right? Because we have a spread from 1999 to 2014. Remember when we look back to Armenia, we saw that we had 2000, 2005, and 2010. But here in Azerbaijan, we only have 2006. So for some countries, and Albania, we only have 2008. So for some countries, we're only going to have 1 observation. For some countries, we may have 2. For some countries, we may have 3. We could run a group by summarize to figure out what the maximum number of countries we have is, right? We could say IPv group by country, summarize n equals n. We'll call it count to be less confusing. The n function will just count how many observations are within each subset, right? So by country, that'll give me a count. And then I can arrange. And I want it to be descending. I want the top number at the top. Count. And there we go. Okay, so in Peru, I have 7 observations. Uganda, I have 6. Egypt, I have 5. Sorry, I'll put this code up in the console so you can see. Check observations for country. Okay, so we can see that actually we have a lot of countries with 4, 5, 6, one with 6, one with 7, right? And then if we remove the descending, let's see how many we have at 1. A lot at 1, right? So for those countries with only 1 observation, we're not really going to be able to make inferences about changes within the country over time, but maybe we could treat them as a higher level of aggregation. Maybe we could treat them as observations within a region rather than as solely observations within a country, right? So sometimes we can aggregate up to increase our power to think about trends. Okay, anyway. So let's look at what these measures show. Again, these are surveys about women's attitudes toward intimate partner violence in these countries. So I've taken the 4 survey measures from the data. These are based on women's responses to survey questions. And then we've done a summary over each of these. So let's kind of look at what we have here. Let's start with no media. What do we see going on here? First, we have 13 missing values. So 13 country years we don't know. We don't have information. What about the rest of these statistics? What's this? We got this. What is it? So this is actually in percentages already. So this is 0.8%, right? 0.8%, the minimum observation of the data in any single country is that only 0.8% of women say they have no access to media. So in some countries, less than 1% of women say they don't have regular access to media. The largest value is 86%, right? So when I look at this, I know that the range on this variable is going to go from what to what. The theoretical range is 0 to 100, right? Because it's on the percentage scale. So a range of 0.8 to 86 is quite large. There's a lot of what I would call variance across countries with a range like that, right? There's a broad spread. We can also see this though, maybe this maximum is a bit misleading. Maybe there's only 1 or 2 countries that are like this. The third quartile tells us the value. What does the third quartile tell us? Yeah, so this is the 75th percentile. So 75% of the values in the data fall below this number, or less than or equal to this number. So even though we have a maximum of 86, the overwhelming majority of values are below 43, right? More than 75% of values are below 43, and more than 75% of values are above 11.25, right? 75% of the data is above the first quartile. 75% of the data is below the third quartile. That means 50% of the data is in this range, 11.25 to 43.23, right? Half of the data falls within this range. And that's a lot less spread than this spread, right? So this tells us we have a small number of cases where no media is very low, a small number of cases where no media is very high, and then a lot between the range of 11 and 43. So that's what this plot can tell us right away. This mean, the relationship between the mean and the median. Anyone want to guess why the median might be slightly higher than the mean here? What does that tell us about the distribution of these variables? How do means respond to outliers? They get pulled down by extreme values, right? Because we're adding them all up and dividing by n, whereas the median is just, okay, 50% of the values are above, 50% are below. So what this data set looks like to me, just looking at these numbers, we'll plot it out in a second, right? If this is 0 and this is 100, we're going to say the peak of this should be at 28.4. We're going to say that the tails on this are a bit longer on the right side than the left side. There's more mass close to 0 than there is, there's more mass below 28.4 than there is above 28.4, and the mean tells us that, because the mean is below the median. Right? These are not things you necessarily need to have strong intuitions about yet, but looking at these 5 numbers can actually tell us a whole lot about the distribution of a variable. Okay, let's do the same thing with secondary schooling. What do we see here? And again, this is the percentage of women who have, let's look at the exact definition, with secondary or higher education. So women who have completed high school or above. What do we see? Maximum 74.6%, the minimum 3%. 50% of the observations fall between 10 and 35. Right? So the bulk of the observations are kind of on the low end. Right? The median here is 22, the mean is 24. In this case, we have the opposite of what we had last time with the mean above the median. Meaning we have some high value cases that are pulling things out. Right? So we have a little bit more going on that side. If these plots don't make any sense to you yet, don't worry about it. These are called density plots, and we're going to start to talk about what these look like and how we can turn this into this. Because ultimately, we want a visual is going to communicate a lot more information. But we can see that the range on this is a little more compressed, right? 35 to 10 as opposed to 11 to 43. Anyway, but the distribution is kind of low. The maximum value in here is 74, 75%. Okay, similarly, for these two variables, we could describe the maximum and minimum range, but then the maximum and minimum aren't always necessarily the most interesting thing for us to look at. The most interesting thing for us to look at might be kind of where is the central tendency in the data. We call these measures of central tendency, the mean and the median, tell us where the center point of the data is. And then measures of spread tell us how variable is the data around those central tendency, right? So we have a first quartile and a third quartile to tell us. Another measure we could use to tell us about spread is what? We talked about it last time. Standard deviation, right? The standard deviation can tell us how different on average is an observation from the mean. And that's a direct measure of the variability of the data set. Yeah.
So current features out would have close to normal distribution.
I don't know. We would need to look at that. The mean and median are similar. We hesitate to call anything normal just eyeballing something like this. And even then, the best it would be is approximately normal. Nothing actually, these variables by definition cannot be normal. Anyone want to guess why? You don't know what a normal distribution is yet. We haven't even talked about it. That's fine. A normal distribution's theoretical limits are negative infinity and positive infinity. These variables have a cut point at 0 and 100. No values below 0, no values above 100 are possible. So by definition, these can't be normal because values above 100 and values below 0 are not possible. Whereas in a normal distribution, any value is theoretically possible. They just become very unlikely at the extremes.
It would probably be the closest to normal based on this.
Don't know. And actually, you know, there's a lot of distributions we could use. Well, that's more of a next semester thing, but there's a lot of different distributions that could capture something like this. I would say this is constrained to 0, 1. So the logistic distribution might do really well for something like this, or a logistic function might map this really well. There's a lot of different things we could do. I don't want us to start thinking too much about, because what we're doing with if this is a little advanced, that's okay. But sometimes what we want to do to understand a process is to say, you know what, this process probably looks a lot like a probability distribution that I know about mathematically, right? So if I think this process should follow the basic properties of a normal distribution, then I can use what I know about the normal distribution to make guesses about what's going on with this variable, right? Now, that's next semester in an intermediate, you'll talk a lot about what's called the generalized linear model and lots of different what are called likelihoods, which are probability functions that we can use to describe data in different ways. It's a little advanced for where we are right now, but let's kind of bookend that. First, we're going to do a little bit of a deep dive on missing data. We've seen this a little bit already. We've seen it in the homework, but I want to kind of work through it explicitly now. So to treat missing value as a single, to treat missing data as a single value, the character is N, capital N, capital A. That has special meaning in R, and that will return the value NA. A plus A, if A is assigned to be equal to missing, is nothing. We don't know what it is, right? NA, not applicable, but effectively, R doesn't know what that value is, so it cannot do mathematical operations with it, right? If you add anything to an NA, it will return an NA. A times 2 likewise will be NA. We don't know what that is. It's undefined. Is A true? I don't know. So we're going to get a missing back. Is A NA? Yes. Okay, so it works like other kind of logical operators, but obviously we can't evaluate true false statements other than is missing. Now, this is one we actually use a lot. I know it looks kind of weird, but not is NA. So the exclamation point will return the opposite of a true or false. So this evaluates to true. And then not says, give me the opposite of that. So let's turn it to false. Not is missing A, false. Because A is missing. It is not missing. Double negatives get confusing, but this is actually a really useful statement for the reason of removing missing data from data frames. So we can have missing data in vectors, right? We have a 2, 3, and a 4. Let's look at what this looks like as a vector. Not Mick, cool. Okay, so we have a 2, a 3, an NA, and a 4. Now, what's going to happen if I type sum of my cool vector? What does that operation do? 2 plus 3 plus NA plus 4. What's that going to return? NA, because it doesn't know what to do with that, right? The mean of it, likewise, will be missing. Now, we could obviously compute the mean without the NA if we drop it first, right? But we'll come back to that in a second. The minimum is also going to be missing, right? Because that NA could be like 1 or negative 300,000. We just don't know what it is. So we can't compute a minimum. But for any of these summary functions, R has an argument called na.rm that we can include. So we can tell R explicitly, do you want to include missing values in the computation or not, right? Because a lot of times we still want to know what the mean is if you exclude that missing value. So if we go back here, we try sum of my cool vector. I'll start typing and you'll see it'll say na.rm. And there it'll tell me that that's when it comes up in purple like this on the autocomplete, that tells us that this is an argument in the function that R knows about. So when it comes up like this as a purple little rectangle there, that tells us this is an argument that's already defined for the function that you can use. Here, I'm going to put na.rm equals true. I could also just put t, and you see it changes to pink. That is R telling me that's a special value that it understands. Right, the pink values here, 2, 3, and a 4. R is telling me it understands what these are. When it's pink, it understands what it is. If I say tree, notice it turns white. R doesn't know what that is. That's an object. Maybe I've defined it, maybe I haven't. But I like to just use TNF for true and false. You can spell the word out if you prefer. Might be easier at this stage, so you can kind of read it a little more clearly. But there's the sum, right? 2 plus 3 plus 4 is 9. na.rm will allow us to compute that. Remove na.rm and we can't. Yeah, we've seen this already, but kind of working through the logic of it a little more intensely now. Again, we could take the minimum now, right? na.rm will work for mean, minimum, standard deviation, sum, maximum, any of those functions that take a vector and return a single value, which we're going to call summary functions. Are na.rm is an argument that you can use for just about any of those functions. SD, okay. So in practice, what we'll see often, is what we're going to be doing in tidyverse, right? So here, I want to compute the mean of the beat burn food variable, and we'll call this the bad version of the good version, right? We can see on the bad version, I'm not including the na.rm flag argument, and so I get an na back, right? Here I do include it as part of my argument within summarize, right? So within summarize, I'm going to define this variable as the mean of this variable, removing missing values. And there I get an actual value back rather than a missing value. So we can use it like this within tidyverse call, or this is, yeah.
The beat burn food and those type of variables, those are all yes or no percentage, right?
These are all percentages, yeah. So here they're aggregations of binary variables. So of course the survey question is this acceptable, yes or no? And then they average that across the country. But when we average zeros and ones, we get a proportion, which we can multiply by 100 to turn into a percentage. So that's what we have here, is the country level percentages. Okay, so if we want to count how many missing values there are in a particular variable, we can sum over isNA, right? Because isNA is going to return a vector of true and false. Let's actually look at this for a second. So let's take my cool vector and let's add another missing to it, okay? So let's do is.na my cool vector. Anyone want to guess what that's going to return? What is in a my cool vector going to return? It's going to return false, false, true, false, true. Check that out. Right? Because the vector now takes on values of 2, 3, NA, 4, NA. NA is going to evaluate each element of the vector. So is this NA? No. Is this NA? No. Is this NA? Yes. Is this NA? No. Is this NA? Yes. So we're going to get false, false, true, false, true. Now, what is false equal to implicitly? Numerically. False is equal to 0. True, you want to guess, is equal to 1. So if we take the sum of a vector with trues and falses, what are we getting? What's that? We'll get with the sum of a vector of zeros and ones. And so what is that going to be equal to? It'll be equal to the number of ones. Two, right? Because 0 plus 0 plus 1 plus 0 plus 1 is 2, right? So R implicitly converts logicals into binary, into 0 and 1, into those numeric values 0 and 1. So if we take the sum of a logical vector of trues and falses, we're going to get back the number of trues. That can be really useful. For example, we could take the number of missing values, sum is NA, beat burn food, and the end function, we'll just count the number of observations total, right? So we're going to divide the number of missing values by the total number of observations in the vector to get the proportion of missing values in the vector. So this tells us that 20.5% of the values are missing, right? Or 31 over 151. That can be really useful, right? 20% that's a lot. But if it were like 70%, if I'm thinking about, do I want to believe this when I remove those missing values to compute a mean, right? So if I remove 20% of the values and compute the mean, odds are pretty good it's still close to what the mean would have been if those values were not missing. If 90% of the values are missing and then I compute the mean, the odds are very bad that what I'm computing would be close to the truth, right? If those values were not missing. So it's always a good idea when we have missing data to just do a quick examination of how much of the data is missing, right? To give us a sense of how reliable what we're looking at should be. I do a ton of work on missing data. And this is the kind of, this is actually something I don't advise doing in like real data analysis, but for now, this is what we're going to do. And this is actually what's done all the time in academic work, but there are much better approaches to take to missing data that, you know, we'll kind of, that's something that will be talked about a little bit next semester. And if you take advanced courses, missing data analysis, it's a complicated topic, but it's something that we can actually do quite a lot about. Okay. So a few different ways to filter out missing values. One that gets used sometimes, I recommend you never use it, is NA omit. What NA omit will do is it'll take the data frame IPV and remove any row with missing values on any variable. So we had 151 rows to start, right? After I run NA omit, I have 116, right? So I've dropped 35 rows. And if we look at the data, I can use the view function to kind of pull up a spreadsheet view within RStudio. Never run view within a markdown document though, because it'll cause a crash because it doesn't know what to do with that. If you want to just look at it, I usually use head. Maybe we can see something on head here. Oops. Not really there, but let's see. Yeah, so here, okay, so for this 2007 observation for Bangladesh, right? Let's say we use NA omit, but we're not actually analyzing this variable. We're analyzing these two variables. NA omit will still drop row 7. But in doing that, we're discarding perfectly good information on these other variables, right? So NA omit is a little too aggressive. Same thing here for the 2004 observation. We have missing values here and here, but if we're interested in learning about these two columns, then dropping this row entirely is throwing out perfectly good information. And the last thing we want to do as data analysts is throw out good information, right? We never want to throw away information. If it's good, right? I mean, missing values are not necessarily good, and sometimes there's measurement error that we know about, and maybe we want to throw that out. But in this case, we're going to assume those are good measurements, and we really want to do everything we can to preserve as much information as possible. Okay, so NA omit, just pretend I didn't even tell you about it. Don't use it. But you'll see it sometimes. That's a really aggressive approach because it's going to throw away information. It's when I say aggressive, I mean it's going to throw away data that it does not need to throw away, right? The better way to do it is by variable, right? So if we know that we're interested in this feed burn food variable, we can combine our not is NA with filter. So what that's going to return, right, is, let's see how this works in practice. So not is dot NA IPV $ eat burn food. So that's what that returns, right? Is a vector that's 151 long, because that's how many rows there are in the data set. What does this tell us? Row 1 is not missing. Row 2, not missing. Row 6, missing. Row 7, missing. Right? So when I run this through a filter, what information is R going to use to decide what to do? I'm going to use this. It's going to say, okay, filter on this condition. So this will be retained. 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 This will not be retained. This will not be retained, etc. Right? So whatever our logical condition is in our filter statement, it'll retain the truths and drop the falses. So in this case, we retain 4 extra observations by only filtering on the one variable, right? With NA omit, we got down to 116. With the filter on only the one variable, we're at 120. It's always a good idea to have more observations. If you trust them, if they're good observations, larger N is always better, right? Because that'll shrink uncertainty and also reduces the likelihood of bias, right? If missing data might be whatever. It's good to have a larger N. I'll leave it at that for now. Okay, so that's how we can do filter is, and I understand a lot of you already did this on your homework, but kind of working through how it works. I feel like it's not bad. Okay, so now let's visualize the distribution of single variables. Okay, these are called univariate visuals. Anytime we're talking about doing something with a single variable, we can call it univariate. If it's with two variables, we'll call it bivariate. If it's with more than two, we'll call it multivariate, right? But univariate visuals. And first so the kind of visuals we're gonna choose will differ based on what kind of variable we're talking about. So what's a categorical variable? We haven't really used this term yet, but a categorical variable is a variable that takes on different values within qualitative categories, right? So this doesn't necessarily fall on a numeric scale. It's something where the units have qualitative differences from each other, so we can think of like color as being a categorical variable, right? The color could take on values of red, blue, green. Now, of course, we could think of ways to represent color numerically, right, as like intensity or hue or something like that. But if we're going to just use the names of the colors, red, blue, green, what about individual names, right? Individual names can't take on a numeric value without some kind of code, right? So index a name to it wouldn't make any sense anyway. A categorical variable really doesn't have a natural scale to it generally, right? An unordered categorical variable doesn't have a scale to it. There are ordered categorical variables. For example, young, old, and senior, right? Or young, adult, child, adult, elder, right? We might think of these as categorical, where the numbers are a little fuzzy in terms of where they might line up. But one thing we could do here, we have some obvious categorical variables in this data set. Region, right? Region of the world is a category, right? There's no numeric kind of ordering of it. It's not continuous, even if it were. So when I say continuous, do we understand what we mean by that? We have discrete and continuous values. Discrete values have breaks between them. There's a clear line between them. Continuous values flow into each other, right? So anything on a decimal-based system is continuous. It goes on forever in both directions. Integers are also continuous, right? They can go from negative infinity to infinity. Discrete values, actually integers are not continuous. Sorry, take that back again, the math. But anything that has space between values, right? Clear space between values is discrete, right? And categorical values are discrete and non-numeric, right? If we want to be precise. But in this case, Asia, Latin America, Middle East, and Central Asia, Sub-Saharan Africa, these are categorical values within the variable region. Region is a categorical variable. In R, sometimes you'll see these called factors. That's the default type for categorical variables in R. We're actually not going to use factors very often. We're going to use character variables instead, because they're a little less cumbersome, a little less tricky to work with. Typically, whenever we see factor, we can just understand kind of intuitively that we're going to be working with a character type variable. That is, the value is Asia. The value is Latin America, right? The value is not 12. The value is Asia, right? And it's easiest, a lot of data sets you'll get have an index code where like Asia equals 1, Latin America equals 2, Middle East and Central Asia equals 3, Sub-Saharan Africa equals 4. That's a factor. When we have a categorical variable mapped onto integers. That's what a factor is. But you can see why that is kind of unnecessary if storage space isn't a problem for us, right? Because like it's easier to just read Asia. It's easier to just read Latin America than it is to read 2 and remember that that's Latin America. The reason historically this was done was to compress file sizes, right? So I can give you a code book that tells you 1 is Asia, so I don't have to have these 4 characters, which takes up space in a file, but storage is cheap, so we don't worry about that anymore. It used to be that storage was not cheap, but now it is. Okay, and so a lot of the stuff in like programming, you'll see a lot of it was built out when like computation and storage was harder, but now it's not. We have what would have been a supercomputer 20 years ago sitting in front of us, right? So we're all good. Okay, so, oh, right, I didn't actually tell you what this was. So in a ggplot call, we saw this in week 1, but let's kind of think about it again. For a ggplot call, ggplot is the plotting function we're going to be using more or less exclusively in class. It's not base, it's part of tidyverse. And GG stands for grammar of graphics. It's a kind of philosophy about data visuals. You don't need to know that, but that's where the GG comes from. So ggplot, first we give it the object that we're plotting. So we're plotting the data frame IPV. This is almost always going to be a data frame. Okay, so we're going to ggplot data frame IPV. AES stands for aesthetics, right? These are aesthetic parameters. So these are parameters, these are pieces of information within the data frame that we are going to aesthetically convert into a visual. So we're going to turn information into a visual. We're going to map the values. What we draw on our graph depends on the value of each row for region, right? So this is going to convert the data into visual. Once we've done that, we've said, okay, the aesthetic parameter you need is region, and that's equal to X, right? So the X value for whatever I tell you to do next should be determined by region. Then I'm going to add a geom to it. A geom tells ggplot what to draw with that aesthetic parameter. In this case, I want to draw a bar, a geom bar. This is a bar plot, and it's the simplest way to represent the distribution of a categorical variable. What do we have here? Right on the x-axis, we have region, and implicitly, geom bar, its default is to put counts on the y-axis. We could change this to proportions with an argument if we wanted to make it not a count of the data, but what percentage or proportion of the data is in each category. But here we can see in Asia, we have like 25 observations. Similarly in Latin America, Middle East and Central Asia, like 19. Sub-Saharan Africa, like 85, right? So, but eyeballing this, what do we see? The bulk of the observations are in Sub-Saharan Africa, and for the rest of the regions, it's about evenly distributed. Yeah? Okay, so this plot actually tells us a lot about the data set, right? Now, realistically, this plot does not convey any more information than this visual. So this is a case where the visual is not necessarily more informative, right? A table that just counts up how many values are in each region conveys the exact same information as that plot, right? All that plot's doing is giving us a bar that's equal to the height for each of these numbers. There's nothing more in that. So typically for these kinds of variables, I prefer to show just a table. But the bar plot is how we could do this. And of course, we could make more complicated bar plots that can actually be quite informative. For example, if we had 12 categories, it might be hard to visually inspect a table, but it might be really easy to visually inspect a bar plot, right? When the number of categories gets larger, the visuals become more informative. Okay, so this is the anatomy of the call. We're going to say ggplot, the object, AES, the aesthetic variables, and these could take on a lot of different things. The ones we're going to see most common are X and Y, but we can also include color as a parameter. We can include shape as a parameter. Sorry. And then the geom to plot those aesthetics, to convert these parameters into a visual. Okay, so everything we do in ggplot is going to take this basic shape. Object, aesthetics, geom. Object, aesthetics, geom, right? The plus in ggplot works exactly the same way as the pipe in tidyverse. The only reason that ggplot doesn't use the pipe is because of some legacy programming stuff in R. It just wouldn't work. But it works exactly the same. Plus here works the same way as pipe when we're doing things like group by summarize or mutate filter. It sucks that they don't use the same exact format, but it's the same idea, right? We're stringing together different pieces. We're stringing together different functions. For example, we could map two things on here. So we're going to ggplot the object. I'm going to give it two aesthetic arguments this time. X is equal to region, and fill, that is the color that I want you to fill the thing you're drawing with, is also equal to region. And then a geom bar. So let's ignore the bottom part of this for a second, right? So now we have the region label as one variable here as an axis, but we also have it as a color. And it's going to give us a legend for that color automatically. Then I also coordinate flip. I flip X and Y. So I'm going to turn, I'm just going to pivot it 90 degrees. Right before we had region on the X. What if I want region on the Y? Well, I could do a coordinate flip. And then I can use XLab to make a label, my cool new axis label. Right? We can customize this to no end. Right? And so like for an average graphic for a paper that I write, probably has 20 to 30 lines of code on it. Right? So, and each of those is just giving different arguments to customize the look of the graphic. We can get really fancy with this. It's one reason why, again, I know I already told you this, but this is one reason why I think learning R is incredibly valuable if you're going to do data analysis, is because the visual capabilities are better than we can get anywhere else. Other than maybe Python, but certainly better than like what you could do in Stata or SAS or SPSS or any of the other kind of routine social science data analysis tools. Okay, so we can also nest transformations within ggplot calls. This is getting a little busy, but I just want to show you what we can do. Remember that this first thing we give to ggplot is just a data frame, right? So I can do a group by summarize as I send it to ggplot. So I can group IPV by country and region and compute the average secondary schooling by country and region, right? So let's look at what that data frame looks like that we're going to pass into ggplot. All right. Come on. Where is my typo? Okay, there we go. I don't know why it wasn't working, but now we had 151 rows in the original data. Now we're going to have 65. We're going to have one row for each country, right? And then we're going to get the cross period average for the secondary school variable, right? So we've compressed 151 rows down to 65, right? We've flattened over time. We've kind of reshaped the data to flatten it over time. And this is what we're going to do now, is I'm going to take this new object I've created that has the variables country, region, and secondary school. And I'm going to put X as country. I know it's on the Y here because I flip it, right? Because when we have a large number of categories, it becomes impossible to read if we keep that on the X-axis, right? This is also impossible to read, but we can imagine with a bigger plot, it wouldn't be. Y is equal to secondary school. Color is equal to region, right? So now visually we can kind of inspect where the purples, the reds, and the blues cluster, right? And we can also look at individual country values. They're alphabetized here. this is not a good plot, right? For lots of reasons, but like, let's look at it in what it would look like if the dimensions weren't horrible. Right, that's a little better. And we could also use some helper functions. What I'll typically do is arrange these so that the highest values are on the top, and then we get them in descending order, right? So an example of a visual like this that we could do, told you that I use this stuff a lot. Right. So this is a ggplot, right, where we take like 20 counties and then sort them by value, right? And we can see that this becomes much easier to read when we have like 20 to 30 categories, and it's especially once we arrange them by the value on the x-axis here. But this is basically the same plot I just showed you. I faceted it here, so we have it by different groups. But this is not much more complex than what we just did. Okay. So far, let's take 5. We got 1058. Let's come back at 1103.
Difference between, so like when you
Sorry, everybody. Forgot to start recording again. Okay, so the histogram for our beet burn food measure and for the density for our beet burn food measure, we can see that we're capturing roughly the same shape, right? We have a peak on the left-hand side, which means in this case close to 0. When we say a left-hand peak, we mean that there's values toward the left side of the x-axis, which typically means smaller values, right? So we have a lot of mass. And when I say mass, what I mean is what was the count of cases that fall on what side? We can describe that as the mass. Typically, mass is kind of a term that we're borrowing from calculus to think about what proportion of the area under the curve. But we can think of that as what proportion of cases, where do they fall? And I would say that we have a left-handed peak here, which means that the mass is higher towards 0 than it is above the mean, right? Because over here, we have a long right tail, right? We can see that this tail on the right-hand side goes out for quite a while. And what that tells us is that we have a small number of cases with very large values, right? The curve doesn't stop here, right? It continues going out because we have a handful of observations with extreme values on this measure. That tail is long. That means there are extreme values, but there's a small number of extreme values. So the tail stretches out, but the bulk of the mass is on the left-hand side, clumped up between 20 and 0. It's not quite at 0, right? Because if it were, this peak would be here. Instead, the peak is right about, I don't know, 8, 7 or 8. And that's going to be, typically, the peak on this will be the mean. No, well, not in this case, because it's not symmetric. If it were symmetric, it would be the mean. But this is the mode, right? The mode is the most common value in the data set. So this is the modal value right there. The mode is the most common. The mean is going to be the exact midpoint, which I believe is actually going to be right about here. For a normal, the mean will be the center. Sorry. Yeah, okay. So histograms and densities. When we have a continuous variable, the first visual that I recommend you producing is a histogram, right? It gives you a really quick sense of what's going on with the variable. You will look at a lot of histograms. Box plot is another way we can represent continuous variables. Now, a box plot I actually find less useful, but some people really like them. So you'll see them, and I kind of want you to understand them for the sake of literacy. But what we have here is a plot with this box with a line through the middle. This box represents 75th and 25th percentile, median. I believe these are 95th percentile ranges, and then these are outliers. So this kind of shows us the distribution of a variable in a more compact way, basically with less ink on the paper than does a histogram or a density, right? It gives us similar information, shows us the bulk of the mass is in that region we were pointing to, that we have a few extreme outliers, right, with long tails, right? But that 75% of the mass is below 22 or so, right? So this kind of gives us a visual of what that summary table would give us. You know, minimum, maximum, 25th percentile, median, 75th percentile, maximum. This gives us a similar set of information. It doesn't represent each data point in the same way, right? Here, right, each data point is included in a pretty direct way in the information we're looking at. So there's more information in a histogram typically than there is in a box plot, right? In the box plot, we have 1, 2, 3, 4, 5, 6, 7, 8 pieces of information here, right? Whereas here, in this histogram, I believe, I don't know, whatever, there's 20 bars there, right? So here we have 20 pieces of information, but we also have the height on them. So we're getting a little more than that. Okay, but you'll see box plots. Again, we have the kind of 5th and 95th percentile, the 25th, 75th percentile, the median, and then any outliers that fall beyond those. In this case, we don't have outliers because the 95th percentile is at 0, right? Nothing can be lower than 0 by definition in this data set.
What is the horizontal?
Nothing.
Mix of it? Is it just? Okay.
They're nothing. The horizontal is, in this case, it doesn't represent anything.
Isn't it normally shorter than that? That's a pretty long.
It is. That's just the dimensions I set for this plot. Yeah, it's kind of funky looking. If I were to just make this, it's because of the shape of my slide. But let's see what it looks like in the R window. It actually doesn't look that different. But you know, the dimension on the X doesn't mean anything.
Okay, gotcha.
Right? Y is the only thing we've set here. And you can see that Y is where we have variation. Okay. Now, let's look at, actually, so the box plot has a cousin called the violin plot. That's kind of interesting. That does a similar thing to the box plot, but also gives us a density. GM violin. Never mind. Maybe we won't look at this. Yeah, okay, we'll look at that in a second. Okay. So bivariate. So we talked about univariate for categorical variables, bar plots, dot plots. Right, this is a dot plot. I use G on point for it. Sorry, I didn't define that. But a dot plot and a bar plot are doing the same thing. It's just, are we representing the count with a bar or with a dot, right? But it's the same information. Histogram for univariate continuous, or density plots for univariate continuous. Next, for bivariates, 2 variable data visuals. We have a lot. Now we're getting into lots of options, right? Because we want to plot 2 categorical variables against each other. We want to plot a categorical against a continuous, 2 continuous variables against each other, right? Each of these situations might call for different kinds of visuals. So 1 continuous, 1 categorical. We could, for example, do a box plot by region. And here's where things start to get more useful, right? So we can see here what the ranges are for each of the regions, where the medians are for each of the regions. And this gives us a sense of kind of like what the distributions across places are. So for example, we can see in Latin America, right, the tolerance for intimate partner violence when a spouse burns the food is quite low. And there's nowhere that it's above, 15% or so, right? At least in this survey. That almost all of the variation is between like 0 and 5%. right? It's really low there. In Asia, I suppose actually the black bar must be the mean, I'm sorry, because otherwise it would be exactly in the middle all the time. So the black bar is the mean. The average in Asia is quite low, but we do have some countries at the higher end, right? At that 75th percentile. And we obviously have an extreme outlier here. And the 95th percentile extends relatively high. So the average is quite low, but we do have some countries on the higher end, right? We have long tails here. Again, we would have that shape where the bulk of the mass is on the left-hand side with a very long tail, right? The Middle East and Central Asia, we actually have a little more symmetry here, right? The mean is kind of close to the middle of this 25th to 75th box. We do have some extreme outliers here too, though. So this isn't going to be quite as bunched up as this one. In this one, Sub-Saharan Africa will be pretty symmetric, right? We'll have about as much mass above and below zero. We do have some outliers here, but yeah. And let no one ever tell you that an outlier is something to be dropped, right? Outliers are valid information. Just because it's an outlier does not mean it's not valid information. It just means it doesn't necessarily look like the other data points. But if it's valid measurement, that's valid information. So never drop outliers unless you have reason to suspect that it's mismeasurement, right? Sometimes you'll hear people talk about dropping outliers. That's nonsense. Don't do that. Okay. The violin plot is a way for us to combine the idea of the box plot and the idea of the density plot. Here you can see that we've actually just got a symmetric density. So the density is just that curve. We just kind of give you the mirror image of it on top and bottom. It's called a violin because it kind of has the shape of, you know, a guitar or a violin or something. So here, remember we described Sub-Saharan Africa as kind of having like a symmetric but long-tailed shape. We can kind of see that here, right? It's a really slow, gradual curve with long tails. We describe Latin America as being heavily bunched up towards zero with a few observations over here. And that's what we see, right? Middle East and Central Asia, we described as having you know, kind of more symmetry than Asia, but still quite long tails. Asia, we described as having quite long tails, right? And we can see here, here, and here, right? We have a tail that goes out very far because we can see those outliers, right? So the density plot needs to incorporate those. We've got extreme values here, here, and here. Most of the mass, right, in Sub-Saharan Africa falls between 40 and, I don't know, 10, right? Between about 30 and 0 in Middle East and Central Asia, between about, what, 15 and 0 in Latin America, and between about 22 or so and 0 in Asia. Yeah.
So would the distribution of Sub-Saharan Africa compared to the other countries be because the sample would the sample size have a part in that distribution? Given that
The sample size is going to smooth out the density.
Okay.
So we know we have more observations here. So it's going to smooth out the density. We're going to have less. You can see here that this shape is a little irregular. We could expect that if we had more observations, the shape would be more regular.
Okay.
Typically with the sample size, we get smoothing. With increased sample size, we get smoothing. But the sample size has nothing to do with necessarily the range.
Okay. That's what I was thinking.
Yeah. No, the range of it, I mean, by chance, we could miss an outlier, or by chance, we could miss an extreme value if our sample size is small. But there's no systematic reason why the range would be smaller.
Just the distribution.
The shape of the distribution is going to be kind of lumpier with a small n and smoother with a large n. Typically.
It doesn't invalidate the comparison.
No. The place where sample size is really going to come in is when we start to talk about uncertainty and we talk about the precision of our estimates. If we're interested in computing, how certain are we about the mean of Sub-Saharan Africa versus the mean of Latin America? Well, we have a lot of observations in Sub-Saharan Africa. We don't have as many observations in Latin America. So I probably have more certainty about the mean in Sub-Saharan Africa than I do the mean in Latin America, right? And we could represent that with a confidence interval. We'll get there later, right? But an n will larger, more observations decreases uncertainty. Okay, assuming, okay, this is a crap plot, but we could create separate plots by some categorical variable. Let me actually do this. Have I shown you all faceting before? I don't think I have. Okay, so I actually want to show you this. There we go. So one thing, and I think this is actually an incredibly useful type of plot, just do a facet. So I'm going to change this to be by region. But let's look at the density, which will be similar to the violin plot I just showed you, but rather than looking at them all on one plot, what's going on? All right. That just doesn't work. I keep trying to run the same thing that doesn't work. Okay, so our violin plot gave us this, right? But maybe we want to look at these on the same scale or on their own scale next to each other, right? And the facet can be one good way to do that. So rather than looking at these as a violin plot, we could look at these as individual densities. So here, right, we can kind of get the same kind of information as we got in the prior plot, but just looking at them individually as densities rather than as, but we can also do that with histograms, right? So faceting allows us to break up, to create separate plots of the geom we've described for each value of a categorical, right? So in this case, what we've told R to do is to do the function facet wrap, which means to kind of wrap the plots within a single kind of grid by region. This tilde says by, just like when we did case when, right? This is the kind of assign it. That way the tilde says facet wrap by region. So we're going to take, if we remove facet wrap, what we'll get is a single plot for the globe, right? Every country. If we include facet wrap, we're going to get a plot for each region. So we can subset it by the values of the categorical variable using facet wrap. So if we want to, for example, look at, we've done group by summarize to look at the values of the average for different groups. Let's say we wanted to look not just at the average for different groups, but the distribution across different groups. Group by our facet wrap and a histogram or a density is a great way to do that. There's a little bit of a downside with the density plot here. We can see that places where we have no values for Asia or Latin America just have nothing on the plot here. When we do this with the density, because the range is defined to go out, we actually do get lines. It's unclear to us looking at this. Is that 0 or is that really close to 0? Right here, it's non-zero, and we can tell that. Here, it's hard to tell whether that's non-zero or 0. So that's not really desirable. In this case, the histogram, I think, is a little more informative because those are actually just zeros. Right? Okay. So faceting, super handy. So I tried to do it by country there, and there's too much, but let's see what it looks like. And let's do it as a histogram. In some cases, there's only going to be one, so it's not going to look great for those. This is going to take it a second because this is a complex visual, and we're going to want to zoom in on it. But I actually do use visuals like this quite a lot for like the 50 states, right? If I want to look quickly at the distribution of something across the 50 states, this can be a good way to do it. If I have 2 dimensions, I want to look at it on. Give me my zoom. There it is. Okay, so that's by country, right? So here we kind of get a sense of the distributions across countries. Remember, for Peru, we had 7 observations, and they were all real close to 0, right? For Ethiopia, apparently we have 3. We get a bit of a spread. For Benin, we have 3. We get a bit of a spread. For the DR, we have a couple, 2 or 3, and there's really close to 0 there. Senegal, apparently we have 3 as well, bit of a spread. Yeah. So this can kind of visualize the histogram for each individual country. If we want to get a sense of like how much information do I actually have access to within each country and what does the distribution look like, this can give us a great sense of it. You want to comment on whether I should be looking at making inferences for individual countries here? Definitely not, right? We're talking about, at best, a very small number of observations for each country. But aggregating these up to the region, I could probably learn something. Yeah.
So that's what I was going to ask. For the region, would that basically show that in sub-Saharan Africa, maybe women are more okay with, or would think that it's more reasonable?
That's the inference we're going to get. Now the question is, how uniform do we think that region is? Right? So when we look at, yeah, that's what our statistics are going to push us to say. And this is why it's really important to look at the visual, is that the average, right? If we do, let's kind of talk about what we get out of this. So if we do IPV group by region, summarize, mean equals mean. Okay, we're going to see that the average here is clearly higher, right? 20.9. And we can see that here. But when we look at it as a density plot, it's not to say that every country in sub-Saharan Africa is above 20.9. That's clearly not true, right? We have a whole lot of observations below 20, right? We have a lot. This is a really spread out distribution. So what does that tell us about sub-Saharan Africa? There's a huge range. There's a lot of variation, right? So this tells us that across countries and perhaps over time within countries, there's a lot of variation, right? The countries are not especially similar to each other. Versus Latin America, right, where we have very little spread in the distribution. These countries are very similar to each other. In each of the other regions, we have a substantial amount of spread, right? And the way we could capture this numerically is with the standard deviation, right? And as a standard deviation is going to tell us how similar are these countries to each other within regions. So we can see that we actually have the highest standard deviation in the Middle East and Central Asia, right? We have the most variation within the group there. But compared to Latin America with a standard deviation of 3.5, we have a pretty big standard deviation in sub-Saharan Africa. The average observation is 13 points away from the mean, right? The average observation is, plus or minus 13 away from the mean. That tells us that there's a lot of swing there. We based on this number, right, we could expect to see values of 7 or 33. That's a huge range. You can see that this actually goes negative here, which doesn't make any sense. But we're using the idea of a normal distribution here, and that's not necessarily accurate for what we're reading off the standard deviation is. But nonetheless, spread is really important. If we just look at the averages, we're missing part of the story, right? In Latin America, we have a story of homogeneity. All the countries are pretty similar to each other. In sub-Saharan Africa, the Middle East and Central Asia, in Asia, we have a story of diversity. The countries are really different from each other, right? And so it's your job as a statistical analyst to not get fixated on a single number, to really explore the complexity of the data, right? And to not misrepresent the average is higher here, but that doesn't necessarily tell us that everywhere in the continent, the values are higher, right? Yeah, so we want to, this is why data visualization to me is so critical, is it helps us at a glance get an insight into what's going on, right? It helps us understand every single data point. It gets us a look at every single data point rather than looking only at one summary statistic like the mean, right? A visual can communicate everything going on in the data set. Unless it's like this, and then you're like, well, that doesn't tell me anything because it's a bad visual. What if we have two continuous variables? So that was categorical bicontinuous. We could do facets, We could do like an X by Y violin plot or bar plot or something like that, right? Box plots, we could do a lot of different things. Two continuous variables. The most common one we're going to see is a scatter plot. So the scatter plot takes two continuous variables, this aesthetics, an X and a Y. In this case, we're going to put the beat, burn food as beat goes out. X-axis here, Y-axis here. We're going to just plot in a kind of Cartesian way the values of X against the values of Y. All right, so for this data point, the value on X is about 18, and the value on Y is, I don't know, call that 18 as well. Right? So we can kind of trace out values on X and Y, and then we put a point exactly where that is. And this shows us the variation in the two variables simultaneously. Right? When we look at this, what do we see? I've added a line on here to kind of help us think about what I want you to look at when you look at a scatter plot. I want you to see, is there some kind of relationship going on between the X's and the Y's? And when we say some kind of relationship, typically the simplest form of a relationship we can look for is a linear relationship. Right? So do we see, when we plot these out, do we see that there's a line that might pass through those points? And if so, does that line have a slope? What do we see here? And how would you describe this line? For low values of beet burn food, we typically see low values of beet goes out. For high values of beet burn food, we typically see high values of beet goes out. We see a positive slope, right? There's a positive association between these two measures. When one of them is high, the other tends to be high. When one of them is low, the other tends to be low. And we're not inferring a causal relationship here. We're saying there's an association. When one is low, the other is likely to be low. When one is high, the other is likely to be high. We can look at the spread to get a sense of that too, right? Like how much spread is there around this line? It's pretty compact, except when we get into this extreme range over here. And there's not many observations over there. But when we're looking in this kind of mid-range, low to mid-range, they're pretty packed in around the line, right? We don't see, for this variable, when we're at 25 here, we don't really see anything above or below 25 here, right? So these two are moving together. These two variables are definitely associated with each other. A scatter plot can tell us a ton, right? A scatter plot visualizes every single data point in the entire data frame, right? We have 151 rows in here. Everything with a non-missing value is included in this plot. So we have like 130 some data points on this plot. And I've used this geom smooth method equals LM to plot the line on top of it. You don't necessarily need to do that, but it helps us kind of visualize what we're looking for when we look at a scatter plot. Now, if we just saw like a random cloud with no clear structure to it, that would suggest no association, right? If there was no clear increase or decrease as we move across the x-axis, if the values of y are kind of all over the place across values of x, right? If we saw if we spread these points out up here, these points out, these points out, these points out, these points out, we would say there's no association. So here is secondary schooling. What can we see here? Someone take a look at this plot and just tell me what you think this tells us. We have secondary schooling on the x-axis and the burn food variable on the y-axis. Someone describe the basic pattern of this plot. You speak a little louder. Yeah, so we have an inverse relationship, right? So there's an inverse proportional relationship here. So can you say what that means in simpler terms? That as secondary schooling increases, the tolerance for intimate partner violence decreases. We have a negative slope here. The slope of the line is negative. That means for low values of secondary schooling, we expect to see high values on the burn food variable. right? Places where secondary schooling is close to 0, the values are clustered above 15. Places where secondary schooling is quite high, the values are typically below 15. We have some weirdness going on here, and I think that's like the Gulf Emirates. But yeah, we have some kind of things that break the pattern, and that's important. That's not to say this is mismeasurement, right? It just means that the pattern doesn't explain everything, right? So that's kind of when we see outliers like this, we're like, okay, there's clearly something going on here, but then there's like a lot of high values over here. There's some low values over here, and then there's some high values over here. So this association is there for sure, but it does not explain everything. We do not know for sure what the burn food variable will be if all we know is secondary schooling. Right? That's one way we can think about it. Predictive power, right? That when we think of associations, we can think of like, if I know one thing, how much does it tell me about the other thing? And in this case, it tells us something, but it does not tell us everything, right? We still have some spread. This one's a little tighter, right? This one, if we know one of them, we more or less know the other. The statistical measure we would use to capture this is the correlation coefficient, which we'll get to that later. We'd say this has a higher correlation than this. But yeah, we'll talk about that as we go. Okay, we can also add a third variable onto the plot. So we have our scatter plot, right? What if we want to add region onto this? We can add a color, right? So we could take the secondary school. We still have the same X and the same Y. But now let's add color for region. So we can start to visually think about the differences across regions on the association between these two variables, right? And so we can see in sub-Saharan Africa a real spread, right? Where we tend to see the bulk of the cases have relatively low values for secondary schooling, but they're all over the place on the tolerance for intimate partner violence, right? And we can see that basically all of that heterogeneity that we were looking at over here, we're like, okay, there's a lot going on here. That's diversity within sub-Saharan Africa on the intimate partner violence measure in terms of toleration, right? But we tend to have low secondary schooling levels. And then as we go, we can kind of see, right, that we have Latin America, these green dots tend to all be clustered regardless of secondary schooling level. In Latin America, we tend to see low tolerance for intimate partner violence across the range. There's still a slope there, right? But it's not as pronounced as it is here, right? We can start to imagine drawing lines through each of these colors of dots. And we can actually do that if we want quite easily. We're getting into the territory of a multi-level approach to this, which is pretty advanced, but I think it can be really useful to look at. So let's look at the Geom Smooth. We're going to do a method equals LM. That stands for linear model. So I just want to plot a line onto it. It'll tell me it's using the y by x formula. And this is kind of an ugly plot. So let's put this SE equals false on that. I think it's SE equals that. Yeah. So now we can kind of look at the structure of the line across regions. And we can see that in the Middle East and Central Asia, based on this data, we don't really see much of a relationship between secondary schooling and the intimate partner violence measure, right? Regardless of secondary schooling, we see about the same level of toleration for intimate partner violence, right? It's pretty steady around 10. In Latin America, we have a shallow slope, but there is a negative relationship here, right? As secondary schooling increases, burn food tends to decrease. In every other region, the slope is steeper in sub-Saharan Africa and Asia, right, than it is in Latin America or the Middle East and Central Asia. So we can start to really finely dissect our data and to look at patterns across variables within the data using just a scatter plot, right? Questions on this? You're going to get practice with this stuff on homework. This is like one of those things that you're just going to have to practice a lot and a lot and a lot, and go back to the slides for reference on how you could do different things. I don't expect you to like fully understand this yet. This is something you really have to just kind of make a bunch of plots to get comfortable with. But we can do a ton with a relatively small amount of code. We can also facet wrap it. This is something I like to do a lot, again, is to facet wrap the scatter plot by region. So the color is kind of cool, but this is busy, right? And if we had more than 150 data points, which is all we have here, that's a small data set. Usually we're talking about thousands of observations. If I used color to try and do this, I would not be able to read it. But if I facet it, I can definitely read it, right? Rather than looking at them overlaid, I can break them apart. And now I can look at individual scatter plots by region. And similarly, we added the line. Let's do that again, just so we can kind of see the comparison of this plot to what it would look like with the line in a faceted version. I tend to think of the facets as a much neater way to look at these things. Oop, 2 pluses. And there's, so we could compare, right, this plot and this plot contain the same information. But because we're breaking things up into distinct groups rather than relying on our ability to tease out color, this one's much easier to read as far as I'm concerned. Yeah.
Could you still add color, like the same?
Sure.
You could still go by color and facet wrap it.
Yeah, I mean, it doesn't add information at that point. It just makes it look pretty if I think that's something that helps. Sure. I can do that. You know, again, the color is redundant with the facet in terms of information, right? Color doesn't actually add anything other than maybe it adds aesthetics, and that's okay. Maybe I don't like that legend, and then I could do fancy stuff like theme, legend, whatever. I could remove that legend if I want. I forget the exact code to do it, but I could remove this piece right here. If I don't want this, I could remove it, right? We can customize like crazy.
Can you change the color of just the line?
Sure. You want to get fancy? Okay. Color equals pink.
I think it's harder to see like with the line the same color.
Oh, sure. I see that. Yeah.
Yeah, that's
So that, but notice here, I changed color equals blue here. This is not aesthetic, right? This does not map on to anything in the data frame. It's static, right? For everything in the data set, it's blue, right? For example, if I go into GeoMPoint, let's remove that here. I could say color equals green. Make all the dots green. But that's not mapped onto anything in the data, right? So if I want to have a visual property mapped on to a variable in the data, I need to use an aesthetic. Tons of flexibility here. Basically, if you can think about something you want to do to the plot, you will be able to do it. That's just a question of figuring out the code, which I'm telling you 90% of the time, if you Google it, there will be an answer on Stack Overflow with how do I do this in ggplot. Someone will have done what you want to do before. Okay. So homework is going to be practiced with dplyr and ggplot for visualization. Do you guys want to do some exercises together real quick, or do you want to call it quits here and just take it to homework? I have some exercises that you could work on with me in the room. Would you like to do that? How about optional? If you want to take off, you can take off. If you don't, we're going to do some practice. Okay, so here are some exercises using the IPV data that I would like you to try if you don't need to go. If you do need to go, no worries. But let's go ahead and try these out. And just throw your hand up if you want me to come take a look. So. You're doing both. So this is called a script, and this is called console runs things from this one. The console, or the script though, is our kind of set of instructions that we're going to write. That's the script. It's the console. Script is kind of like a file with a few instructions. Yeah, that's right. So what we want to do before we you type library. Did you install that package? Parentheses, no, parentheses. And now hit command enter on that one. Okay. Now, can you go, are you on Slack? You go, I gave you a URL from Slack. So just right click and copy that. Copy the URL, copy link address. Go back to type IPv. Something you have on my yeah. And then do underscore DLC. Type of quotation. Maybe see what you do it down, paste it in that below. Now take that and have the data set in. Now the console is where we can treat that like a sandbox, where if you just want to like experiment with something to check out what's going on. Just scroll down to your console. Click on the bottom of that. And click home. Purchase fields are lower. Remember head function on now give us the first 6 rows of data set, just so we can get a quick look at what's inside. Just need that URL down. Yeah, and the data on the homework assignment is actually so there, where you can just see some data on this. So from here, can you try to do the filter to remove the missing value? Free data transfer ID. No. So you just need to move on up to maybe a line 10. I thought that was IPv in the system. We're just going to create one by assigning. We're going to start by modifying your IPv. The object we're starting from is which is map shift. And that's what we're new missing values. Filter. Actually, I still like this app if you don't have to. But it's a type filter. Remember, and then remember how you not missing? Open the parentheses after his name. It's SEC underscore school. There's one more close parentheses after that. You can see the X on that. That's not, it's not quite done. At the very end. So keep doing the close parentheses. Good. Now, check it. How do you check the number of words? So type on the console, click the console. And row on the first object on IPv. Parentheses. Info on just, we created this new object called IPv. That works on that. So it's already stored in your computer. You can see that we have 3 more rows than the one with the missing values, then you go to the one without. So you drop this one. So that's what question 1 asks. So you created a new data frame called IPv no missing that filters out the ones. Yeah, sorry, I'm just going to stop my recording. I don't need to